Now, as mentioned, Niels Bohr did do the calculations for what these different energy states are, and therefore he would be able to calculate what the difference in energy would be when an electron goes from a higher energy state down to a lower energy state. Now, as I say, when the electron goes from a higher to a lower energy state, energy is lost as light, and in other words, as a particle of light, in other words, a photon. The energy of that photon can be calculated, and in turn, the wavelength of that photon can be determined. So let's run through the calculation. And what I'd like to do is look at a particular transition. So I'm going to make use of this particular equation, which is found on your formula sheet. And note it says the change in energy of the atom is equal to this number, negative 2.178 times 10 to the negative 18 joules. And then it depends on what the difference in energy levels are. So NF stands for the final energy level, and NI stands for the initial energy level. For instance, if we look at the transition from 3 down to 1, so this would correspond to the transition number 2. So we're going from level 3, the electron's there, down to 1. Now you'll see that there's a spot in your course pack to actually fill out this calculation. I do other calculations for you, but I'd like you to focus right now on that transition from 3 down to 1, and I've labeled that transition number 2, for instance. So I plug in the values into my equation. So N initial, in this case, is equal to 3. And so I've written down here 3 squared. N final, of course, is equal to 1. In other words, the ground state. And so this is why I have written 1 squared down there. If we continue with this calculation, if we subtract 1 over 3 squared, in other words, 1/9, from 1, we end up with 0.8889. Now, the significant figures here is a little bit tricky because these n values are exact integers. So I'm going to let the 2.178 dictate the number of significant figures. So I'm going to use 4 significant figures. I keep on with the calculation, so that would be the change in energy of our atom as the electron falls from a higher energy level state down to a lower energy state. Note that the sign here is negative. This is quite significant. This means that the atom is losing energy, exactly as we would expect when the electron falls from a higher energy state down to a lower energy state. Now, we're going to continue. And one of the things that I want to point out is, yes, the atom is losing energy. It's losing energy according to the photon that was lost. And so it must be that that photon has the same energy that was lost by the atom. And it's important to distinguish the change in energy of the atom and then the energy of a photon. So we can't talk about the change in energy of a photon. It is just of a particular energy. So the atom loses that amount of energy. How does it lose that energy? Well, it loses it as a photon. So note, I've taken that delta E atom and I've, in a sense, made it into a positive value. In other words, we can say that the energy of a photon is equal to the absolute value of the change in energy of our atom. So there we have the 1.936 times 10 to the negative 18 joules. Now, once I have, of course, the energy of a photon, I can calculate the wavelength of that particular photon. This is the same calculation that we saw in the chem activity number 18. So I'm starting with the equation, the energy of the photon is equal to hc over lambda. And I'm just solving for lambda. So lambda is equal to hc times the energy of the photon. So of course, h is the 6.626 times 10 to the negative 34 joule second. Then I have the speed of light. And then I have that energy of the photon that I just calculated. And I find that the wavelength is this 1.026 times 10 to the minus 7 meters. It's easier to convert this to nanometers because then we can relate to the visible portion of the electromagnetic spectrum, which is of course 400 to 700 nanometers. So I'm going to change this now to nanometers, 102.6 nanometers. Now you might reflect for a minute, where would we expect to find this in the electromagnetic spectrum, given that the visible portion again is 400 through to 700 nanometers?